Hello, hi everyone. Welcome to this online video classes. This is Dr. U. Raghavinder, Assistant Professor of Chemistry, MVS Government Degree and PG College, Mahabub Nagar, Telangana. Today in this video, I would like to explain about part 3 of coordination compounds. Till now, I developed two videos on coordination chemistry or coordination compounds. In part 1 of coordination compounds video, I explained about the introduction, importance of coordination compounds, as well as about the terminology which is used in coordination chemistry. In part 2 of coordination compounds video, I explained about the nomenclature of coordination compounds as well as some small theories or some theories such as Werner theory, Sedgwick electronic theory, and also I explained about the effective atomic number and the Sedgwick concept. Okay, fine. Next, in this video, I would like to explain about the theories of coordination compounds. There are so many theories proposed by different scientists. Among them, I would like to explain the first theory, that is valence bond theory VBT, in this video. In valence bond theory, I would like to explain the postulates of the theory and applications of VBT to 4 coordinated complexes as well as 6 coordinate complexes. And also I would like to explain about the limitations of VBT. Okay, fine. Next, here the first one, valence bond theory. Generally, it is valence bond is theory is proposed by Linus Pauling. Okay, in order to explain the formation of complexes, their structures, and bonding nature in between the metal and ligands, there are so many theories proposed by different scientists. Among them, the best one or the important theories which explain the bonding features as well as structures of coordination compounds or complex compounds. The main theories are, the first one is valence bond theory, second one is crystal field theory, third one is molecular orbital theory. These three theories generally considered as metal ligand bond theories. Considered as metal ligand bond theories. Okay, in this video I would like to explain about the valence bond theory. It is proposed by Linus Pauling in the year 1931. Before the proposal of VBT by Linus Pauling, there are some theories proposed to explain the bonding features of the coordination compounds, as I discussed in the part 2 of coordination compounds video. That is mainly the main theory one is Werner theory and Sedgwick electronic theory. Before that theories, that is Sedgwick and Werner theory, there is also one theory, Bloomstrand Johannesburg chain theory. Okay, but these theories, that is Bloomstrand Johannesburg theory as well as Werner theory and Sedgwick theory, they don't explain all the properties of the coordination compounds. They have so many limitations. So in order to overcome those limitations, in the next years many scientists proposed this metal ligand bond theories. Among them, valence bond theory is one of the important metal ligand bond theory. It is proposed by Linus Pauling in 1931. This theory, that is valence bond theory, explained successfully the structures as well as the magnetic properties of so many coordination compounds. According to this theory, the central atom or ion generally uses or utilizes n-1d ns-np orbitals, or it may use ns-np-nd orbital in order to undergo hybridization in the presence of or in the influence of ligands. Okay, these hybrid orbital which are formed during the hybridization process of metal atoms. These hybrid orbitals undergo overlap with the filled orbitals of the Ligand's donor atoms in order to form the corresponding complex compound. Okay, this will be explained in the following table or following examples. That is, the number of coordination number as well as the structure will be explained in the next slide according to VBT. Okay, fine. Next, here, based on the coordination number, the coordination compound or complex compound may get different polyhedron, coordination polyhedron or geometry. According to VBT, the structure or geometry of the complex compound with various coordination numbers generally depends on the hybridization of the central metal atom or ion. That is mainly based on the hybridization concept. Linus Pauling explained the structures of the complex compounds. Okay, this table depicts the structure and hybridization relationship. If the coordination number is 4, then the hybridization may be sp3. In such case, the geometry of the complex compound is tetrahedral. If the coordination number is 4, similar to the above, then if the hybridization is if dsp2, then the structure or geometry of the complex is square planar. That is, the four coordinated complex may have two different structure based on the hybridization. So hybridization is important in order to obtain the particular geometry to the complex compound. So if the hybridization is sp3, it is tetrahedron. If the hybridization is dsp2, it is square planar geometry. Okay, in the case of five coordinated complexes, or that is coordination number is 5, then the hybridization is sp3d, then the geometry is trigonal bipyramid tbp. If the coordination number is 6, then the hybridization may be sp3d2. In such case, geometry is octahedral. If the coordination number is 6, then the hybridization may be D2sp3 instead of sp3d2. In such case also the geometry is octahedral. Okay, this is about the hybridization and geometry relationship based on the coordination number. Okay, fine. Next, sorry. Next, the postulates of the valence bond theory. It is proposed by Linus Pauling in 1931. In order to explain the bonding features in the complex compounds, he put forward his ideas in the form of VBT theory. There are some postulates in the VBT theory. Those postulates are, the first one is, according to VBT, the metal ligand bond is covalent bond. That is, the bond is covalent in nature. According to Sidgwick, it is ionic, but according to Pauling or VBT, the metal ligand bond is covalent bond. Next point. Here, the central metal atom or central metal ion generally provides or makes available the number of vacant orbitals equal to the coordination number of that particular complex. That is, the central metal atom or central metal ion in the first step provides a number of vacant orbitals in order to undergo hybridization after that to form the corresponding complex compound. Okay, these vacant orbitals generally undergo hybridization to form an equal set of hybrid orbitals which are arranged in a particular geometry around the central metal atom or central metal ion. Due to this particular arrangement of the hybrid orbitals, the complex compound or coordination compounds also get that particular geometry after its formation. Okay, fine. Next, here the vacant orbitals, which are situated around the central metal atom or ion in a particular geometry, undergo overlap. This overlap is generally end-on and overlap with the filled orbitals of the Ligand's donor atom in order to form the corresponding complex compound. Okay, fine. Next, here valence bond theory is generally applicable to study the bonding features or the geometry of the four coordinated complexes as well as six coordinated complexes. The first one, application of VBT to four coordinate complexes. Here the VBT, that is valence bond theory, successfully explained the bonding features of four coordinate complexes based on the hybridization process or hybridization phenomena. Generally here the VBT, valence bond theory, generally explain the geometry or bonding features of the complex compounds based on hybridization process. Okay. In four coordinated complexes, they may have tetrahedral shape or they may have square planar geometry based on the hybridization of the central metal ion or atom. Following explain this contradiction, that is whether the four coordinated complex whether the four coordinated complex contains whether it contains square planar geometry or whether it contains tetrahedral geometry. If the complex is four coordinated complex, it is generally based on the magnetic property or magnetic values. That is based on the magnetic values. He explained the tetrahedron or square planar geometry of the four coordinated complexes. Okay, fine. It is mainly based on the magnetic property values of the complex compounds. Okay, next, here if the central metal atom ion or ion central metal atom or ion undergo sp3 hybridization, then the geometry of the complex is tetrahedral. If it undergo dsp2 hybridization, then it gets square planar geometry as we discussed in the previous slide. Okay, fine. Next, here the first one is application of VPT to tetrahedral complexes. That is the complexes in which the central metal atom or ion undergo sp3 hybridization. Okay, in tetrahedral molecular geometry, generally the central atom or central ion located at the center or at the corner of the tetrahedron, and the four ligands generally occupy the four corners of the tetrahedron. They occupy the four corners. That is the central metal atom situated or located at the center of the tetrahedron corner, and the four corners occupied by the four ligands. Generally the tetrahedron geometry is widespread. That is, most of the complexes or most of the compounds generally have tetrahedral geometry. But in the case of inorganic compounds or in the case of complex compounds, generally the metals with d8 electron configuration generally forms tetrahedral complexes. Okay, in tetrahedral complexes, generally the central atom or central metal ion utilizes 1s 3p orbitals during the hybridization process. That is, the central metal atom or central metal ion undergo sp3 hybridization by utilizing 1s and 3p orbitals and produces four equivalent sp3 hybrid orbitals which are arranged in tetrahedral geometry around the central atom or ion. If you observe the example for tetrahedral complexes, maybe tetraamine nickel ion or tetracarbonyl nickel or tetrachloronickelate ion. There are so many examples. Other examples maybe tetraamine zinc ion, tetracarbonyl nickel, so on. Okay, next. If you take a specific example in order to study the bonding features of the tetrahedral complex according to VBT, the example is tetraamine nickel ion, that is tetraamine nickel ion plus 2 ion. In this complex, it is a tetrahedral complex. In this complex, the central metal is nickel. Generally, it is present in plus 2, nickel plus 2 ion. Here, that is the central metal ion is nickel plus 2. This nickel plus 2 undergo sp3 hybridization to form 4 sp3 vacant orbitals around the nickel plus 2 ion in a tetrahedral geometry. That is, the nickel plus 2 ion undergo or undergo hybridization by utilizing one s orbital and three p orbitals. Generally, they are vacant orbitals to form four sp3 hybrid orbitals which are occupied in a tetrahedral geometry around the nickel ion. These four sp3 vacant orbitals undergo overlap, that is end and end overlap with the filled orbitals of the ammonia ligands, or but in particular they undergo overlap with the four nitrogen donor atoms of the four ammonia ligands to form sigma bonds or covalent bonds. Thereby the complex, that is tetramine nickel complex ion, is obtained. Here the bonds generally covalent due to overlap and on and overlap. Here the complex, if you observe the complex structure, it is tetrahedral geometry. If we observe the magnetic property, here the magnetic property of the complex is generally it is paramagnetic, because in the complex compound nickel contains two unpaired electrons, so it is paramagnetic. Generally, substances based on magnetism classified into different types. They may be diamagnetic, paramagnetic, ferromagnetic, or antiferromagnetic. In the case of here, in the case of chemical compounds or compounds, generally it is based on the presence or absence of unpaired electrons. If the compound or species, chemical species, contains all paired electrons, then it is diamagnetic. If it contains at least one unpaired electrons, then it is paramagnetic. If it contains more than one unpaired electrons in the same direction, that is, all the unpaired electrons have same type of spin arranged with the same spin, then it is known as ferromagnetic. If the compound or species contains more unpaired electrons, but the arrangement is random or zigzag, then it is known as antiferromagnetic. Okay, here in the nickel compound, that is tetramine nickel complex compound, the complex compound, that is the nickel metal ion, contains two unpaired electrons, so it is paramagnetic in nature. Okay, fine. Next, so observe the formation of the complex according to BBT. Here in this compound, that is tetramine nickel plus 2 compound, this its central atom is nickel. This atomic number is nickel atomic number is Z equal to 28. Here the outer electronic configuration of nickel is 3d8 4s2 4p0 4d0. If you take in this complex compound, nickel is in plus 2 oxidation state. So if you observe the nickel plus 2 outer electronic configuration, then it is 3d8 4s0 4p0 4d0. That is, it loses 2s electron, so it is 4s0 in nickel plus 2 state. If you observe the electronic configuration in tetraamine nickel complex ion, then it is 3d8 4s2 4p6 4d0. It is due to the overlap of vacant 4s 4p orbitals with the filled orbitals of the ligands. It's like this. Here the nickel in the plus 2 state or ionic state undergo sp3 hybridization. sp3 hybridization by utilizing 1s and 3 phi orbitals to undergo sp3 hybridization. So due to the utilization of 1 4s orbital and 3 4p orbitals during the sp3 hybridization process, nickel plus 2 gets 4 sp3 hybrid orbitals around the nickel plus 2 ion as shown here. It is generally the orbitals, sp3 orbitals, arranged in a tetrahedron geometry. So this structure adopted by the complex after its formation. This vacant sp3 orbitals of the nickel plus 2 ion undergo end-on end overlap with the filled sp3 orbitals of the 4 ammonia ligands as shown here. Here overlap takes place. So we get this tetrahedral complex compound, that is tetraamine nickel ion. Okay, this is about the structure or bonding features of the tetrahedral complex according to VBT. Here generally the explanation based on the hybridization process only. So based on this explanation, we can also uh, explain the other explain the structures of the other tetrahedral complexes. Okay, fine. Please go through all the tetrahedral complexes. Okay, next. Here, next application of VBT to square planar complexes. That is, in the case of 4 coordinated complexes, the complex may adopt tetrahedral geometry or may adopt square planar geometry based on the hybridization of the central metal ion. Okay, for this square planar complexes, take the example as tetracyanonickelate ion. Okay, now let us discuss the bonding features in the tetracyanonickelate ion according to VBT. In this complex, the central metal ion is nickel plus 2. Here nickel plus 2 undergo electron rearrangement. That is, here nickel plus 2 undergo electron rearrangement in the presence of strong filled ligands. Here cyanides, Cn minus cyanides or strong filled ligands. They are strong filled ligands. So in the presence of strong filled cyanide ligands, there is a rearrangement of electrons in the nickel plus 2 ions. After the rearrangement, the nickel plus 2 undergo dsp2 hybridization by utilizing one 3d orbital and one s orbital and two 4p orbitals to form 4 dsp2 orbitals, which are generally vacant, and they occupy all the 4 dsp2 orbitals occupy the 4 corners of the square plane or square plane around the central metal ion. That is, all the vacant orbitals generally occupy four corners of the square. Here, these four dsp2 vacant orbitals undergo end-on and overlap with the filled orbitals of the cyanide-like bonds to form tetracyanonickelate ion complex. Generally, here the complex is in square planar geometry. If you observe the magnetic property of this square planar complex, the complex has no unpaired electrons due to the electron rearrangement in the presence of strong filled cyanide ligand. All the single electrons gets paired due to this pairing of the electrons in the presence of strong filled ligand. The complex don't have any unpaired electrons, so it shows diamagnetism. Okay, fine. Next, if you observe the bonding features in the tetracyanonickelate ion, here in this tetracyanonickelate ion, the central metal is nickel. Its atomic number is Z is 28. Nickel outer electronic configuration is 3d8, 4s2, 4p0, 4d0. Nickel plus 2 outer electronic configuration is 3d8, 4s0, 4p0, 4d0. That is, it loses 2 4s electron to form nickel plus 2 ion. This nickel plus 2 ion undergo electron rearrangement in the presence of cyanide ligands. So, in the presence of cyanide ligands, the outer electron configuration of the nickel plus 2 is 3d8, 4s0, 4p0, 4d0. In the absence of cyanide ligands, the nickel plus 2 contains two unpaired electrons, but in the presence of cyanide ligands, all the single electrons gets paired, so there is no unpaired electrons in the nickel plus 2 in the presence of cyanide ligands. This nickel plus 2 undergo dsp2 hybridization in the presence of cyanide ligands to form 4 dsp2 vacant orbitals around the nickel plus 2 ion, which occupies in the four corners of the square. Here, the electronic configuration of the complex, that is, electronic configuration of the nickel in the complex is 3d10, 4s2, 4p, 4, 4d0. Here, the four cyanides donates lone pair of electrons to the vacant orbitals of the nickel plus 2. So, as this is the indicates the donation of lone pair of electron from cyanide nucleophiles. Here, the nickel plus 2, by utilizing one 4s orbital, one 3d orbital, two 4p orbitals undergo hybridization to form 4 ds2 orbitals, which occupies the four corners of the square around the nickel plus 2 ion. These vacant dsp2 orbitals around the nickel plus 2 ion undergo overlap with the four cyanide ligands filled orbitals of the four cyanide ligands as shown here to form the corresponding complex, that is tetracyanonickelate complex, which is generally in square planar geometry. In the presence of strong field ligands, all the single electrons or unpaired electrons are converted into paired one. So there is no single electrons. So it is diamagnetic in nature. Okay, fine. There are some other complexes also. For example, the mainly It is uh, zinc tetraman copper complex, as well as some platinum complexes, or example for best example for queer planar geometry compounds. Okay, fine. Next, application of VBT to octahedral complexes. Here, octahedral complexes, or they may be six coordinated complexes. Till now, we discussed about the application of VBT to four coordinated complexes. Here it is application to six coordinate complexes. Here, that is the octahedral complexes. Here the octahedral complexes are two types based on the types of d orbitals utilized for hybridization. If the central metal ion or metal atom utilizes inner n minus 1d orbital and ns and np orbitals, that is, if the central atom or ion utilizes inner n minus 1d ns and np orbitals, then the corresponding complex is known as inner orbital complex. That is, here there are two types. One is inner orbital complex. The second one is outer orbital complex, based on the type of d orbitals utilized during the hybridization process. The first one, inner orbital complex. Sorry. If the metal ion or central metal atom utilizes inner n minus 1d orbitals, then the complex known as inner orbital complex. If in the case of inner orbital complexes, generally, sorry, generally the strong filled ligands form inner orbital complexes. That is, ligands are two types: strong filled ligands, weak filled ligands. The presence of strong filled ligands, generally we get inner orbital complexes. These inner orbital complexes, they may have or they may don't have unpaired electrons. So these complexes also known as low spin complexes. That is, inner orbital complexes also known as low spin complexes, because in the presence of strong pill ligand, all the single electrons or unpaired electrons get converted into paired one. So there is no unpaired electrons, so their spin is generally low. So they are known as low spin complexes. If the metal central metal atom or ion utilizes its outer nd orbitals, the complex considered as outer orbital complex. Generally, outer orbital complexes are produced in the presence of weak field ligands. Generally, weak field ligands are responsible for the formation of outer orbital complexes, and they have more number of unpaired electrons. So they they known as high spin complexes, because in the presence of weak field ligands, the unpaired electrons don't get fed. So we get more unpaired electrons in the complex. That's why the complex is known as high spin complex. Inner orbital complex, low spin complex. Outer orbital complex is high spin complex. The conditions is inner orbital complex generally formed in the presence of strong field. Outer orbital complex generally formed in the presence of weak field ligands. Okay, fine. Next, if you take specific examples for octahedral complexes or six coordinated complexes, in order to explain the bonding features according to VBT. Take the hexaamine cobalt complex ion. In this complex ion or in this complex compound, the central metal ion is cobalt plus 3. It undergo electron rearrangement in the presence of strong filled ammonia like bonds. After that, that is after the rearrangement of the electrons in the presence of strong filled ammonia like bonds, the cobalt plus 3 ion undergo D2sp3 hybridization by utilizing two 3d orbitals and one s orbital and three phi orbitals. So here the complex utilizes or the metal ion utilizes inner n minus 1d orbital, that is inner 3d orbitals. So it is example for inner orbital complexes. Generally inner orbital complex generally found in the presence strong field ligand. So here the ammonia is strong field ligand, so it is best example for inner orbital complex. The other example may be potassium ferrocyanide, potassium pericyanide. So many example we can take for inner orbital complexes where the ligand is strong field one. Okay, fine. Next, here these 6d2sp3 orbitals, that is 6d2sp3 vacant orbitals generally undergo overlap according to VPT with filled d orbitals, with filled orbitals of the 6 ammonia ligands. Here in the case of ammonia, the filled orbital is sp3 orbital of nitrogen atom. Okay, 2. Then we get corresponding complex due to overlap in between the vacant and filled orbitals. Here the complex geometry is octahedral geometry. Here geometry octahedral. Here the complex has no unpaired electrons, so it is diamagnetic in nature. So as we discussed in the case of inner orbital and outer orbital complexes, inner orbital complexes generally formed in the presence of strong field ligands. So in the presence of strong field ligands, electrons, that is single electrons or unpaired electrons, get converted into paired electrons. So there is no unpaired electrons mostly in majority complexes, in majority inner orbital complex. So in majority cases inner orbital complexes are diamagnetic compounds. In few cases, due to presence of one or two unpaired electrons, they may show paramagnetic nature. Okay, fine. Next, if you observe the structural features or bonding features of the inner orbital complex, that is hexaamine cobalt plus 3 ion complex. Here the central metal is cobalt atom. The atomic number is, it is generally 27. If you observe the outer electron configuration, it is 3d7 4s2 4p0 4d0. Here the outer electronic configuration of cobalt plus 3, because here the central atom is in plus 3 oxidation state. So if you observe the plus 3 outer electron configuration, it is 3d6 4 4s0 4p0 4d0. That is, it losses, that is cobalt losses 2 electrons from 4s orbital and 1 electron from 3d orbital during the complex formation. This cobalt plus 3 ion undergo electron rearrangement in the presence of ammonia strong field ligand. So if you observe the electron configuration in the presence of ammonia ligands, then it is 3d6 4s0 4p0 4d0. But here the single electrons get fade, so there is no single electrons, so it shows diamagnetism. Okay, if you observe the electron configuration of cobalt plus 3 in complex compound, it is 3d10 4s2 4p6 4d0, because here the six ammonia ligands donates lone pair of electrons toward the vacant orbitals of the cobalt plus 3. Okay, here the cobalt plus 3 utilizes 2d orbital, 1s orbital and 3 p orbitals to form 6d2 sp3 orbitals, which are occupied 6 octahedron corners around the central metal ion. This 6 vacant d2sp3 orbitals present on the cobalt plus 3 ion undergo overlap with 6 ammonia ligands as shown here to form corresponding octahedral hexamer cobalt plus 3 complex. Okay, fine. Next one is specific example is hexafluorocobaltate ion. In this complex, the central atom is cobalt. It also present in plus 3 oxidation state. So the cobalt plus 3 ion undergo sp3d2 hybridization by utilizing 1s orbital, 3p orbital and 2 4d orbitals. Hence, it is example for outer orbital complex. Here, the ligand fluoride is generally weak field ligand. So, in the presence of weak field ligand, we get generally the outer orbital complexes. So, the hexafluorocobaltate is also one of the outer orbital complexes because it utilizes the outer nd orbital. That is, here the cobalt utilizes outer 4d orbital instead of utilizing 3d orbital, so it is outer orbital complex. Here the 6 sp3d vacant orbitals obtained during the hybridization process undergo end-on and overlap according to VBT with filled orbitals of the 6 fluoride ligands to form corresponding hexafluorocobaltate complex. Okay, next. Here, if you observe the geometry, it is octahedral geometry. Here, the complex contain 4 unpaired electrons, hence, it shows paramagnetism. Here, generally, the magnetic value generally measured, that is mu equal to under root n into n plus 2. The magnetic value generally equal to under root n into n plus 2, where n equal to Bohr magneton Bm, units of Bm, Bohr magneton. Here n is number of unpaired electrons. Okay, fine. Next, here if you observe the structure, here in hexafluorocobaltate, the central atom is cobalt, atomic number is 27. If you observe the outer electronic configuration, it is 3d7 4s2 4p0 4d0. Here cobalt plus 3 outer electronic configuration is 3d6 4s0 4p0 4d0. Here it loses 3 electrons, 2 from 4s orbital and 1 from 3d orbital. Okay, due to the presence of weak field fluoride ligands, there is no electron rearrangement in the central metal ion. So, in this case, it undergo sp3d2 sp3d2 hybridization to form 6 sp3d two orbitals. Here the electron configuration of the cobalt plus 3 in the complex is 3d6 4s2 4p6 4d2. It is due to the supply or donation of lone pair of electrons into vacant orbitals by the ligands. Okay, here cobalt plus 3 by utilizing 1s 3p orbital 2d orbitals, it forms 6 sp3d2 orbitals which are occupied around the cobalt plus 3 in a octahedral geometry. This vacant orbital sp3d2 orbitals undergo overlap with the 6 filled orbitals of the fluoride ligands to form corresponding hexafluoro cobaltate complex as shown here. Oh, the complex is octahedral. It is paramagnetic because it contains 4 unpaired electrons. So it is paramagnetic in nature. Okay, fine. Next. Okay, the valence bond theory explain the bonding features, that is mainly the geometries of the various complex compounds based on the hybridization property as well as by using magnetic values. But there are some drawbacks or some limitations in VBT theory also. That is, if you observe the limitation, the first one is generally the theory involves a number of assumptions. So it take a number of assumptions in order to explain the bonding structures. Okay, next one is it didn't give any account about the color property of complex compound. That is mainly majority of coordination compounds or complex compounds have specific color, but the VBT didn't explain any color property of the complex compounds. Next, it didn't explain the conditions for the formation of inner orbital complex or outer orbital complex. That is, he don't give any specific condition in what conditions the inner orbital complex formed or in what condition the outer orbital complex is formed. Didn't predict the exactly whether the four coordinate complex contains tetrahedral shape or whether it contains square planar geometry. That is, he didn't give any explanation in the case of four coordinated complexes whether it contains octahedral, whether it contains tetrahedral or whether it contains square planar geometry. In order to rectify this contradiction, he used the magnetic property values of those four coordinated complexes. Okay, next one is he didn't give any account about the classification of or about the strength of the ligands, whether a given ligand is strong field or whether it is weak field. That is, they didn't give any idea about the strong field as well as weak field ligands. Next one, he didn't give any quantitative interpretation about magnetic values. He used the magnetic values to study bonding features in the case of four coordinated complex, but he didn't give exact or quantitative interpretation about these magnetic values. Next one, he didn't explain any stability on the complex compound, that is whether the given complex compound is thermal stable or it is kinetically stable. That is, didn't give any explanation about the thermodynamic as well as kinetic stability of complex compounds. Okay, fine. Next, So in order to overcome these limitations or drawbacks of VBT, many scientists proposed various theories. Among the various theories are the crystal field theory and molecular orbital theory, which somewhat explain better level than the VBT in the case of color property as well as Lygon's classification. Okay, fine. Next. Okay, thank you very much for your patience for watching this video. Thank you one and all. Okay, bye.